So in this session, we're going to be looking at two-column geometric proofs. So before we go into proofs, let's just look at certain definitions which are pretty much necessary to define those geometric proofs. So the first one that we have is a postulate. So a postulate is pretty much just like a certain truth that is found in it's just a statement that is a definite truth amongst all mathematics. So for example, the Sas Congruence, which states that if you have a triangle, if you have two triangles with proportional sides, or actually with the same side lengths, and then it's the same angle, and then another side with the same length, that means that both those triangles are congruent with one another. The next thing that we have is a theorem. The next definition that we have is a theorem. A theorem is a statement that can be proven. For example, we're going to be looking at the base angle theorem, which shows how an isosceles triangle has both equal angles and equal side lengths. A corollary, we're not going to be looking into this too much, but a corollary is just a statement which is proven by a theorem. So all corollaries are theorems, but not all theorems are corollaries. And a proof is just a way of justification. So whenever you're trying to justify a theorem, the evidence that you prove for that the evidence that you bring out for that theorem is the proof that you bring in. All right. Let's jump in to the first example. So in this example, we have a figure which shows two different triangles, and we have the fact that segment BD bisects both the angles ABC and ADC. So by definition of like a bisector, we know that the angle here and angle here are going to be equivalent. That's what a basic angle bisector does. It just splits an angle into two equivalent parts. Using that, we're supposed to prove how the triangle BCD is congruent with the triangle DAB. Okay. So in order to do this, we want to be looking at certain two-column proofs. So the two-column, it just refers to like a statement and a reason of how you get to the proof. So it's just like a methodology from what you've been given and then getting down to the proof. So in this case, we are given, the first statement that we have is the given, which is always going to be like something that's already given. So the first statement here is segments BD bisects both the angles ABC and ADC, and the reason why we have that is because it's just a given. Next thing that we already know is because of the definition of an angle bisector or just a bisector, we know by the definition of an angle bisector, we know that angles 1 and 2 are going to be equivalent, as well as 4 and 3. Now, determining whether or not 1 and 4 and 1 and 3 are equivalent, that's a little bit later. So we know that 1 and 2 are both congruent because of the definition of a angle bisector. So we're just going to write that down right here. So angle 1 is congruent to angle 2 by definition of an angle bisector. All right. Now from here we know what else? Something else that we can notice is the fact that the triangle DAB and the triangle DCB or BCD both have a segment which is shared, which is the segment BD. So that is shared between both of them. So we can actually utilize that as like a reflexive property. So reflexive as in all it just says is both the same segment is going to be equivalent to the same segment. So BD is congruent with BD. Which is kind of like common sense, but it's still a certain property in geometry. So it's given by the reflexive property. So properties are similar to postulates, except for the fact that it's not like a certain statement. It's more like, it's just more like an identity of the thing, of the whatever that you're looking at. So if it's like a polygon, it's the identity of the polygon. If it's a triangle, it's the identity of the triangle, etc. And finally, now we do have an actual statement that we can utilize. It's since angles 1 and 2 are congruent. Oh, gotta mention angles 3 and 4 are also congruent by the same definition. All right. So now we have two angles which are congruent in both triangles, or two pairs of angles that are congruent with one another, and we also have a congruent by reflexive property segment. So that's an angle, a side, and another angle. So by the ASA rule, we have the ASA postulate, we have triangle BCD is congruent to the triangle DAB. And that's by ASA. All right, now let's look on to a different problem. Go down to the next problem here. Okay, this is going to be the problem about the base angle theorem. So base angle theorem, it's just the identity of like an actual isosceles triangle. So right here we have a fact that says the segment AD bisects the angle BAC. So it bisects this angle into two equivalent angles. And angle B is congruent with angle C. So this angle right here is congruent with angle C. So that angle and that angle are both congruent. Now, utilizing that, we're supposed to prove that AB and AC are both congruent. So both of these segments are supposed to be congruent. All right, again, the first statement that we have is going to be the given, which is the fact that the segment AD bisects angle BAC, and these angle B is congruent with angle C. Let's fix that. And yeah. So using this, we're supposed to go on with trying to prove that AB and AC are both congruent. So in order to do this, what we can notice immediately is by the definition of an angle bisector, the angle BAD, so this angle right here, is going to be congruent with this angle right here, DA or CAD. So we can write that down as an identity. And that's by the definition of an angle bisector, yet again. So angle BAD is congruent with the angle CAD. And again, that just comes from the definition of an angle bisector. Angle bisector. All right. Now from here, we can notice just based off yet again the reflexive property, since this smaller triangle, the DBA triangle and the DCA triangle both share the segment AD, we can also utilize the reflexive property from the last question to state that AD, the segment AD is congruent in both. So AD is congruent with both, and that's just because it's the same thing. And that's by the reflexive property yet again. Now we see that after we set that, we can state using the angle side theorem postulate, actually, the angle side postulate, that because both the segment is the same for both, we can state that since the angle B and the angle BAD are the same as, are the equivalent to angle C and angle CAD, and both of them share the same side, we can utilize the angle side postulate to state that both of them are congruent. Both of those triangles are congruent. So both the triangles, triangle ABD is congruent with the triangle ACD. Just be a triangle. So let's write down triangle ACD. And it's given by, through the postulate, the angle side postulate. We already looked at. Now we have a congruent triangle. So a fact about all congruent triangles is the fact that if you look at any two corresponding segments between two congruent triangles, they're both going to be congruent as well. So let's say if you have a similar angle, say angle B and angle C are going to be congruent, which is a given between these two triangles. Angle BAD and angle CAD are both congruent. Angle BDA, so this angle right here, and angle CDA are both congruent as well. Same with the facts as segment BD is congruent with segment CD, segment AC is congruent with segment AB, which is exactly what we're trying to prove. So let's write that down. And that's going to be the end of this proof. So segment AB is congruent with segment AC by the corresponding parts of a congruent triangle are congruent. So CPCTC, that's just an abbreviation for what we just mentioned. The corresponding parts of congruent triangles are congruent. I like to remember that with something like cracker, peanut butter, tuna cracker. That's just something I guess I like. But any way that you guys can memorize, it's the best. It's one of the most utilizable postulates here. Now, for this problem, we're given that the segment AC and the segment DE are both parallel. So this sign right here means that they're both parallel. Also given by the two triangles between them. So that just indicates that both those segments are parallel. And we're trying to prove that the ratio between AC and DE is equivalent to the ratio between BC and BE. Remember, fractions can also be written as or considered to be ratios. So the first statement that we're going to have is obviously the given. Same with all the other problems. And from the given, we're going to notice that angle ACB and angle DEB, so these two angles are going to be congruent. And that's because of two parallel lines always having corresponding angles. So the corresponding angles inside it for connected to a transversal between two parallel lines are always going to be congruent. So let's write that down. Angle ADB congruent with angle DEB. Again, you could have just wrote down angle C and angle E, but it's always good to state which specific angle that you're looking at, even though in this case, that is the only angle that you would be looking at. And it's the reason behind that is because parallel lines imply, so a double dash arrow is going to be implies an implication specific based like a symbol for implying something, and it implies that corresponding angles are congruent. Corresponding angles are congruent. And now we have, using the reflexive property yet again, this angle right here, angle B, is being shared by both the triangles CAB as well as DEB. So using reflexive property, we can state that angle B is congruent with angle B. So let's write down reflexive property. And finally, now we're going to notice a certain fact. Two angles that are similar between the two triangles. As you can see right here, that you have a small triangle and a big triangle. The smaller one right here, and the bigger one, which fully closes it. So both of those triangles share two congruent angles. So angle B is shared by both of them, so that's going to be congruent between two of them. And angle E and angle C are both congruent. Therefore, we can assume that both of those triangles are similar by the AA postulate, the angle-angle postulate. So we can assume that triangle BED is similar to triangle BCD. CA. Notice that I did utilize the word similar, and it's only similar. It's similar because obviously both of those triangles are not the same size. Congruent implies that both size and angle are both consistent, or proportionality are both consistent. In this case, only proportionality is consistent. And this is given by the AA postulate, the angle-angle similarity postulate. And finally, through this, we have corresponding sides. Since corresponding sides of congruent triangle or similar triangles are always proportional, we can assume that these segments AC, the ratio between AC and DE, the ratio between the segments AC and DE are going to be equivalent with the ratio of segments between BC and BE. This is because of the postulate that says corresponding sides of similar triangles are proportional. And all this means is AC, the ratio between AC and DE is equivalent to BC over EE. And since we already implied the fact that, we already found out the fact that both of those triangles are similar, we can assume that all lengths have only been increased by a certain factor or a certain proportional rate, which is going to be consistent amongst all the sides. So the rate at which AC, or like the rate at which DE was dilated to become bigger, to becoming AC, is going to be the same as how much bigger BE or BC is to BE. Now let's look at E. Okay. So in this question, we have a given which says, or three givens which state that angle A is congruent with angle D. So angles 1 and 6 are congruent. Angle 2 is congruent with angle 5. And angle ABC, which is going to be this angle right here, is congruent with angle DCB. So it's going to be this angle right here. And we're supposed to be proving how BE, the segment BE, is congruent with the segment CE. All right, let's look into that. Again, like all other problems, our first statement is going to be the givens, or given or givens. The number of givens or whatever it is, it's always going to be our first statement. Our next statement, from these givens, we can find out that angle, we can use the fact that we can use the subtraction property of equality triangles, or the subtraction property of equality theorem, to state that the difference between angle DCB and angle 5 is going to be the same as the difference between angle ABC and angle 2, because both of those angles, their respective angles, are congruent from one another. So here we have, let's write that down. We're assuming that we're going to state that the measurement of angle ABC state measurement of angle ABC minus the measurement of angle 2 is going to be equal to the measurement of angle DCB minus the measurement of angle 5. Notice I did utilize measurements of angles in this case, and that's because we can't really subtract two different angles. We have to subtract their actual values instead. Here, all we're stating is the fact that angle DCB minus this angle, notice angle 4 and 5 are both complementary, and they add up to making angle C. So if we subtract out angle C, or if we subtract out angle 5 from angle C, we're going to be getting angle 4. And we're also saying that since angle B and angle C are both the same, angle B, like ABC, and DCB are the same, angle 2 and angle 5 are the same. We're stating that if we subtract out angle 2 from angle ABC, we're going to be getting angle 3, which is congruent with angle 4, which will be congruent with angle 4. So the property which allows us to do this is the subtraction of subtraction property of equality. All this theorem says is if you subtract out two equivalent things, like if you subtract out 10 minus 2 and 10 minus 2, you're going to be getting the same exact thing. Or rather, 10 minus 2 and 12 minus 10, you're going to get the same exact thing. But in this case, both of them are equivalent, so you can utilize 10 minus 2 and 10 minus 2. All right, and let's look at, all right, from here, we're going to get, as mentioned, angles 4 and angle 3 congruent with one another. So angle 3 is congruent with angle 4. And that's just because of the substitution property. We can substitute the measurement of angle 4, or the subtraction identity between those two, as angle 3 and angle 4. So we're just substituting both of them in. Just for clarity's purposes, it's measurement of angle 3 right here is the same as this angle right here. So the difference between measurement of angle ABC minus measurement of angle 2, that's going to be the same thing as angle 3. And the measurement of angle DCB minus measurement of angle 5, well, that pretty much just represents angle 4. And from here, we can go down to saying that angle 3 and angle 4, since they're both congruent, we can assume that this triangle BEC or BCE, it is a isosceles triangle. And remember from the other problem that we already did, which is the base angle theorem, that is how we got to this position. So since two angles are congruent with one another, we can assume that this triangle itself is a isosceles triangle using the base angle theorem. So using the base angle theorem, triangle BCE is isosceles. finally, since an isosceles triangle is going to have, by the definition of an isosceles triangle, you know that two lengths of which are opposite to its respective angle, they're going to be the same. That's the definition of isosceles triangle. So from that, we can assume we can get the proof, which is segment BE is congruent with segment CE. And again, that's just because of the definition of an isosceles triangle. All right, let's finish it up with one last problem. So in this case, we have a figure which has a given which states the segments AC and BD bisect each other. So this segment right here and this segment right here bisect one another. So BD bisects AC into two equal parts, and AC bisects BD into two equal parts as well. And we're trying to prove that the segment CB is congruent with the segment AD. So we're trying to prove that this segment is the same as this segment. All right. So just based on the definition of a natural bisector, we can state that the segments BC or BE and ED are congruent with one another, and the segments AE and EC are congruent with one another. So we have segment AE segment AE is congruent with segment EC, and segment BE is congruent with segment ED. And that's just from the definition of bisectors. Notice this is not the definition of angle bisector, it's only the definition of a bisector. An angle bisector bisects or differentiates an angle into two equal parts, while a bisector differentiates a segment into two different parts. You can also call it a segment bisector. Anyway, from this, we can also assume that the angle CEB from this diagram, we can assume that the angle CEB is congruent with the angle AED. And the reasoning behind that is because of vertical angles. So both of these angles are congruent with one another, and these two angles are congruent with one another, but we don't really need those two angles. So this angle and this angle are congruent with one another because of vertical angles, and let's just write that down. And again, let's do the vertical angles. All right, now we're going to notice that we have a triangle with a segment of size 2, I guess. I'm assuming that this is size 2 and this is size 1. So a triangle with size 2, an angle, and a size 1, and another triangle with size 2, the same angle, and size 1, I guess. And so from that, you can assume that through side angle side proportionality, that both of those triangles are congruent with one another. We have triangle CEB is congruent with triangle AED by SAS, the SAS postulate, side angle side. Finally, using the cracker peanut butter tuna, cracker peanut butter, cracker tuna, cracker, or the corresponding parts of a congruent triangle are congruent fact theorem, we can state that AD and BC are both, or AC, or no, CB and AD are both congruent. CB and AD both congruent. That about wraps it up for session on geometric proofs. Again, this is all based off of certain postulates in geometry.